is not listening always just in my speech. If you have anything to ask, you're so few, so please come up, ask questions as we go along. You're very welcome to it. So, 16 different parts in an assembly operation. If you make it by additive, you just make it a piece. And that saves money. And also for different parts of industry, it also makes you have smaller inventory. You have much better, you have much fewer parts that can be lost, and can be dust, it can be broken, so it's much safer that way. So, and this has brought some very good, very important benefits. And for example, hearing aids. We all know we are individual people, everybody's different. The shell inside the hearing, our hair, is the ears, is always individual. Traditionally, this was made by actually taking a piece of wax or something like that, put into the ear, make sort of the shape of that, and then take it out and use that as a mold to mold a shape that would be fit into your ear. If you have a process based on additive, you would have you do that wax piece, but then you scan in 3D scan and convert that into 3D geometry, and then you store that in a digital file, so you have it in a digital inventory for that individual patient. That may not sound like such a radical thing, but for example, my dad, who has hearing aids, it broke. Was it split, so it was cracked, and it hurt in his ear. When he went out and asked, can I get a new shell? They said, okay, first you need to come back to the clinic, and we're going to analyze the damage to that and see if you actually need a new shell. And if you decide that you need a new shell, well, we'll discuss that on the next meeting and check if it works with the budget. But if you decide that we actually need a new shell and we can fit it into the budget, you can come back, and then we start to make the casting, and 6 weeks later you could come back and get a new shell. If they had this thing, they would have just said, okay, it's broken, and they could have had it built overnight, and it would be ready, and it would cost less than actually the meeting when they discussed if you needed it. This had had a very strong effect on the market, this benefit. It's not very clear, it wasn't that much money, but when I started to do this, it was around in the late 1990s. It was still, they had started doing it a few companies. In 2005, it was about 80% of the market with this. 2008, it had reduced all other competitive technologies for making these shells for the hearing aids were gone. And those companies, for example, on the United States market, those companies who couldn't change within 500 days are not on the market today. So it can go very, very fast. Another piece, small parts, very, very complex geometries, dental implants. Same thing, you can scan it, you can mold it, and then you can build it. There are about 60 to 100 machines made by one company, I know, US, that are dedicated to just make dental implants. You can make 400 pieces in a 24-hour cycle. In difference, normal technician who could make about 4 with the traditional method of molding and casting. So it's a big difference. And this one is going on, but mostly it's not so much in Europe. It's actually outsourced by European companies, so it's made in other parts of the world, but not for the European market. Hip joint implants. The shell, the cup you put into the hip bone. Normally, if you would do it, you make it in titanium, TiCx4, and then you mill it, and then you have to apply coating to give it a rough surface so that the bone actually has some adhesion of the bone, ingrowth of the bone into that part. The problem is the coating procedure there. First, it's an extra operation you need to do. And then, besides that, you need to make sure that the quality of this coating, the attachment of this coating is perfect. If you do it with additive instead, you just build it, and you build this structure into the part. And you can even design the porosity to encourage bone ingrowth. And that has been, and so it's a part, the porosity, the coating, the rough silk is a part of the actual piece, which means it grows in very well. It's been tailored. You you're safe about it, you're watchless, and it's now been passed as a CE marking. It's FDA approved in the United States and in China, and I think it was in 2016 they passed over 100,000 produced annually of these type of electronics. And tools. If you want to make injection molding tools, for example, instead of making cooling channels, injection molding, you inject plastic into a mold, you need to use shape. The cooling, you need to cool that thing. Channels, normally if you do it conventionally, you have to drill straight holes, plug them, and you're a bit limited in shape. With additive manufacturing, you just make it conformal. You actually make the cooling cool where you want it, more efficiently, more even. It can reduce the cycle times to about 50%, meaning double the production. On the right-hand side, that is a jig, a fixture to assemble just this little sticker on the back of a car. To assemble that, and that takes about, that mold was made by that tool was made by additive. It's about a half a kilo lighter than its equivalent. And a half a kilo lighter, well, that may not sound as so much, but if you're going to lift and assemble several thousand a day, that's a matter of the joints and the shoulders of the operator. And that's a big difference. And you can also facilitate it so it's actually more ergonomically fixed. This is another good thing. It's a gas turbine burner. Gas turbines like a jet engine on the ground producing electricity. You inject natural gas, you combust it, you burn it. It's high temperature, it's highly abrasive environment. So you see the tip there on the left-hand side picture, it's been worn down. It has a very good heat-resistant superalloy, but it will be worn down. And normally when that is worn down, you need to make a new part. That means you have to cut it off, you saw it off, and you mill a new piece with 18, you need to weld something on it, so about 18 different welds, and then you weld it back on. Altogether, that has a cycle time of about 44 weeks to do this repair. Some thought this is too long. So decided to go additive, and then instead of mill off the top, just a few centimeters, and then rebuild the part. That cycle time for repair is 4 weeks. That's a 90% cycle time reduction in this repair. And that has a big impact for Siemens turbo machinery. So they actually built the factory. So what you see on the, they invested about 21 million euros, about at that time currency about 200 million Norwegian kroners in a factory in Finspång in Sweden. So that's how half of it looks, and that is what you can expect from a factory of the future. In the aerospace, since you don't use any more material than you actually need, that means that you can save weight, and you can also reduce the number of parts, the inventory. Boivie company had reduced the inventory with the inventory catalog with about 200,000 pieces by additive. You saw the duct before, there was 16 pieces in one. Well, these are examples which I make. And this is just reduction of the inventory. That's the money saved. They actually save weight too, but that's not really the driving force. All the pieces they need to have together to be in all control, and also the tools to make it. So this is going on fine. But weight reduction saves fuel, since we're talking about the environment today. 1 kilo of reduced weight in a traffic airliner saves about $3,000 of fuel in a year. If you then decide to reduce 1,000 parts with 150 grams, if you take about a large size traffic airliner, that's not too much, that's 150 kilos, which would mean $13.5 million in saved fuel costs in lifespan of the plane. And you think about the planes that will be coming in the next couple of years. They're expecting to have about 28,000 new flight planes will be ordered. That would be $351 billion saved fuel, is fuel cost. And let's think about the carbon dioxide that's going out that's not being emitted either. So it's a big difference. Small changes will make a big difference. And here, as you of course understand, this is just a simple bracket made by Airbus. On the left-hand side, you see the original. It's an aluminum, melted in aluminum. On the right-hand side, you see the additive manufacturing part. It's being made by titanium. It's topology optimized. It's actually, the sections are hollow, so it's actually no more than material than it's needed. So it's between, a little bit dependent on which size model it is. We're talking about a weight reduction of 30 to 55%. This is just one small non-critical part. An airplane has many parts. Another thing is repair. Since you can actually add material, replace that's gone. This is a seal for a Pratt & Whitney jet engine. It has some of these thin lamellas going up in it, which actually seal it up. They're being worn down. If you're going to remake it, if they're worn down, normally you would have to remake the entire piece. But if instead you can do it with additive and actually rebuild it, as you see on the right part. Rebuild the lamellas, you need to mill a bit. And that's been passed and being accepted to be used for 4 different repairs. So a piece that normally would have a 10,000 hour lifespan now has a 50,000 hour lifespan. That's also a big saving. There are, today this is a part in an engine and a moving part. And there are well, in 2016 there had been made about 1,500 parts that have been repaired this way, and it kept on doing it since. If going in further, GE Aviation, well-known company, they have been looking at this for a while, and they decided to look at this fuel injection nozzle for their new LEAP engine. It started out, normally there would be 20 different pieces, now replaced by one piece. They have seen that they have optimized the design, so there's no build-up of coke, actually carbon deposits, there's no coking, thereby prolong the life cycle of this part by 5 times. And also, since this coking doesn't build up, it means the fuel is being burnt more efficiently, so they save even more fuel, and they also have reduced the weight by 25%. In the production passed 30,000 pieces in 2018. And it's also on SAS airplanes. So if you fly SAS, it's quite likely actually been carried by additive manufacturing, only that we didn't know. So there's some fantastic possibilities here, but there's lots of challenges we need to work with. The process and material are connected, are more connected than ever before, and actually in a different way than ever. You need to build knowledge about the relationship between process and materials. There's lots of variables. You need to have them controlled through the process. The properties of each material need to be connected to the setup of the process parameters for each step in the manufacturing process. And with that, we need to make sure that we have quality assurance, traceability, and inspection. How do you inspect? How are you sure if you're going to put a critical part on an airplane? You want to know that it actually will do the job. You won't fall down away. So we need new ways to design. We need new ways to develop new products. We need to learn this. We need to integrate it in the production system and the verification system. We need to check the machines. How can we make the cost go down? How can we get process faster? How can we make them designed for industrial integration to be fit with it? How can we automate manual operations? There's still a lot of hand work there. On the other hand, thinking this is in a high-cost country, it's very nice if we can have people working with their hands a little bit, so there will be jobs for them, for people who will not spend the time too much on the computer screen. And then the raw materials, we need to control that. Cost, quality control, how to optimize it. That's also work that needs to be done. Now, let's go back to the start. People talk about 3D printers for homework. Will this really be the revolution for making things? Well, to begin with, they're fairly easy to use, that's fair. They're available, that's also available. But you need to have the feedstock material. In this case, for the machines being used at home, filaments of plastic. And there's some limitation to which plastic you can use. And you also need to have access to them. and there's different properties you can get out of it. You need to have support materials, you need to remove that. That is also necessary. And then you compare, if you want to have a wider selection here, maybe a milling machine. It costs a little bit more, but you can actually have a lot more materials. And they've been along for a long time. People have been able to buy desktop milling machines for at least 30 years. Most people don't have that, though. I don't, but I know people who have. In comparison, people said, we have the sewing machines. That has not made us make all our own clothes. Yes, I do use a sewing machine. I mend my own jeans with it. I'm not ashamed to say that. Which is known. But it's not the problem, the access of sewing machine that make people buy clothes in the stores. It was not that when everybody has a sewing machine, we'll all make our own clothes. So I'm a bit skeptic about the theory that people will actually make all their stuff, everything they want at home with a 3D printer machine, because there are limitations, and and people actually, you need to be able to work with it too. I would actually place it a little bit on the same level. Sewing machine is a wonderful tool for what you use it for. If you're really interested, you can make your own clothes, you can make things. Same thing with a so-called 3D printer. It's a great tool for what you want to make. You make small, fine plastic parts, but it will not solve all your problems. It's helpful for hobbyists and interested parties, great. Maybe not people at the most. About house then. Well, we have the snails, we have the mollusks, we have the scallops, we have the birds. Will we do it? Possibly. You can build walls quite clearly. Extrusion of a type of concrete. That's very nice. You can make a hollow section, that's also good. There is talk about the giant printer building 10 houses in a day, yeah, sure. But then there's the thing, actually putting up a wall and putting a roof over it, is that enough for a house that people can live in? How about this? Enforcement, environment. Is that these processes, when you extrude a line of concrete after each other, you will not get in this steel enforcement strength in a minute. You need to figure that one out. And that actually will have some effect on the material. And that's not really quite solved yet. We need to think also about how is the load bearing of this material? How will we design for that? How will the acoustics be if you had built the walls for this? What's the vibration properties? Thermal properties, fire properties, moisture transport. There are a lot of issues that need to resolve here. So yes, we can make things in concrete, that's nice. But there's a lot of research to be done before it's being something that we're going to make houses with. But on the other hand, okay, for the time being, you can make wonderful complex shapes, parts, decorations, joint fixtures, special things, but not necessarily the whole building that people can live in yet. Well, I actually had fewer people listening than I started. That's a fantastic testament. Additive manufacturing will not replace all other manufacturing technologies within the foreseeable future, but it's a vital key to innovation. And it's used widely in the world with lots of investments. So if you don't have it, you have a serious back problem. There's hardly one part of society will not be affected in one way or another. It's growing incredibly fast. Interest and investment interest are there, but you need to have knowledge to be able to work with it to do it right. And knowledge is not the same thing as surfing the internet for a few minutes. You haven't seen the top of the iceberg yet, but we have opened the door to new universe in manufacturing. Thank you. Any questions?